Educational Module, Machine Learning, Learning Unit, Advanced. Training Methods. Stochastic gradient descent (SGD) is a training method applied to methods such as SVMs, logistic regression and multilayer perceptrons. The goal is to learn a linear scoring function in order to make predictions. It is called stochastic because samples are selected randomly instead of as a single group or in the order they appear in the training set. Stochastic gradient descent is much faster and more efficient than standard gradient descent, especially on large datasets. The result of using this technique is very fast convergence but also lack of robustness. The parameter update of SGD takes the following form. Optimization attempts to minimize or maximize, minimize in our case, an objective function. In this scenario, the objective function is an error function which is dependent on the model learnable parameters. One simple yet effective rule of thumb to choose the tuning parameter of SGD is to select a small subset of data, try various values on this subset, and choose the one that most reduces the objective function. It has been shown that SGD asymptotically converges to the true minimizer of the estimator. General algorithm for stochastic gradient descent. The main positives are the convergence speed, the overall efficiency and efficiency in large datasets. The negatives are that it requires several hyperparameters such as a regularization parameter and a number of iterations. Also, it is sensitive to feature scaling. Stochastic gradient descent uses a regularization term that penalizes model complexity. Popular choices for the regularization task are the L1 and L2 norm loss functions. The image shows the contours of the different regularization terms in the parameter space for penalty equal to 1. ElasticNet is a convex combination of L2 and L1. Stochastic gradient descent can also be used in neural networks when the training data size is observed to be large. Instead of computing the gradient, each iteration estimates the value of gradient on the basis of a single randomly picked example. A good approach to balance the shortcomings of both gradient descent and SGD would be to use mini-batch gradient descent. The updates are performed for every batch of the original dataset, which includes a constant number of samples, usually the power of 2. Other optimizers include ADAGRAD, RMSprop, and ADAM. In ADAGRAD, the learning rate adapts specifically to individual features, which can be an advantage for sparse datasets but has the issue of the learning rate always decreasing through time and ending up too small. RMSprop attempts to remedy the aforementioned shortcoming of ADAGRAD. Finally, ADAM, the most commonly used one, also computes adaptive learning rates for each parameter. However, it calculates current gradients by storing the decaying average of past gradients while also utilizing momentum. The ADAM algorithm has fast convergence, low variance and healthy learning rate that doesn't vanish. Dropout is a popular regularization technique used in machine learning models and mainly in neural networks. Its goal is to reduce overfitting by preventing coadaptation on the training data. Overfitting, overspecializing on the training data, is a common phenomenon in neural networks because of the added layers of abstraction, which allow them to model rare dependencies in the training data. Dropout is used very often in deep learning tasks and in literature is considered a model averaging method. Dropout creates subnetworks child models aiming to minimize the expected loss by dropping out units. It reduces overfitting in a neural network by preventing complex adaptations during training and excluding rare dependencies from the model. There are certain variations of dropout are the standard dropout, the Gaussian dropout, the variational dropout. The fast dropout is particularly interesting and widely used,